Now let's extend the work energy method for multiple loads case by extending the previous topic. So here we're gonna consider like a relatively simple problem where we have a beam with a simple support at left and right ends, and yeah, we're gonna consider point of force applied on point 1 and point 2. So when we apply both point P1 and P2, both point loads, yeah, we can decompose the problem into two parts. First part with only P1 and second part with only P2. And if we define the deflection of original problem as y1 and y2, and deflection of first problem as y11 and y21, it implies that deflection at point 1 by point P1, and y21 means deflection at point 2 by only 2 P1. So yeah, the first index indicates the position, and the second index is the effect of which loading, like a P1 or P2. Okay, so you can have y11 and y21. Of course, both of them are smaller than y1 and y2 respectively. And for the second problem, we can define y12 and y22. Y22 is the deflection at 2 by only point P2, and y12 is deflection of point 1 only by P2. Okay, so yeah, what we can do is from superposition principle, we can say that y11 plus y12, y11 plus y12 should be same as y1. We can also say that y2 should be same as y21 plus y22. Okay, so yeah, by considering these, y1 equals to be y11 plus y12, y2 equals to be y21 plus y22. Then from here, we can ask this question, like for each of them, y11 is deflection at point 1 due to P1, and this must be proportional to P1, and let's call the proportionality constant as P alpha 11. And y12 is the deflection at point 1 due to P2, and of course y12 and P2 should have a linear relationship or proportionality relationship. Let's call the constant, proportionality constant, as y12. In the same way, regarding y21, we can define alpha 21, which relates the relationship between P1 and y21. For y22, we can have a relationship between P2 and y22 through proportionality constant alpha 22. Okay, so by considering these relationship and plug in the definition of y11, y12, y21, and y22, and we can write down y1 and y2 in this way, like alpha 11 p1 plus alpha 12 p2, and y2 equals to be alpha 21 p1 plus alpha 22 and p2. Now if we stop here, it will be quite tough to use the work energy method. So our next step is we'll try to obtain the relationship between alpha 12 and alpha 21, and based on that, we'll try to extract some useful relationship. Okay, so how can we obtain the relationship between alpha 12 and alpha 21 and other alpha ij constants? So here what we're gonna do is we'll try to achieve the final stage through two different paths. Whether we choose like a path 1 or path 2, whether we choose the path on the left or the path on the right, if the final stage is the same, the energy accumulated should be same. So we're gonna have the relationship between alpha 12 and alpha 21 using this equivalent between path 1 energy and path 2 energy. Okay, so let's consider work done. So the first path will be apply P1 first, then P2, and second path will be apply P2 first and P1 later. So as a first step, for the left part, let's consider applying P1 only. So after applying P1 only, the work done for this structure is there is no force on point 2, right? So work done should be P1 multiplied by y11 multiplied by 1/2, because y11 and P1 will have a linear relationship until P1 reaches to the final stage values. Okay, and in the second step, keeping the value of P1 and as constant because we already reached the final value of P1, and we're gonna slowly extend increase P2 from 0 to the final stage value. Okay, so in this case we have a constant P1 and still additional extension y12, and regarding the the point 2, we have P2 from 0 to the final value of P2 and additional deflection y22. So from this constant value of force, we kept force constant, so the work done is P1 times y12, and from the second one, because P2 increased from 0 to P2, from step 1 to step 2, we have to multiply 1 over 2. If I visualize it better, in step 1 we didn't touch P2 value, we only increase P1 value to the final value, and then in stage 2 we keep the value of P1 and increase the value of P2 from 0 to the final value in linear way. Okay, so we have first work done and we have a second work done. By combining U1 and U2, we can obtain the work done in path A, the path on the left. Then we can do same thing for the path 2, where we have P2 on location 2, so the work done should be half P2 y22 because P2 increased from 0 to the final value, and keeping the value of P2 constant and increase P1 from 0 to the final value. So we have half P1 y11 from the second step, and we have P2 y21 because P2 was kept constant and y21 is additional deflection at location 2. Okay, so if you combine y1 and y2, it will be your total work done or total accumulated strain energy for path B. Okay, so in path B we increased P2 first and kept P2 in the second step. However, about P1 we kept P1 and 0 in the first step and increase P1 linearly in the second step. Okay, so by equating UA and UB from this relationship, and what you can find is that this term and this term are equal to each other, first term, and last term are equal to each other. Only a second term is different. However, because UA and UB should be should be equal to each other, alpha 1 and alpha 21, alpha 12 and alpha 21 should be equal to each other. It is called Maxwell's reciprocal relationship. Okay, so depending on like your choice, you can either specify like alpha 11, alpha 12, and alpha 22, or you can specify alpha 11, alpha 21, and alpha 22. Whatever choice you have, alpha 12 or alpha 21, you're gonna have exactly same value. Okay, that's what this Maxwell reciprocal relationship says. Okay, so now let's consider the relationship. So we already have y1 equals to be y11 plus y12, right? So if we consider y11 plus y12, it should be same as alpha 11 p1 plus alpha 12 p2. Okay, so this is the how we obtain the alpha y1 in terms of alpha and p1 and p2. So if we consider like partial u and partial p1, from the first one, what you're gonna get is alpha 11 p1 plus alpha 12 p2. Okay, so what you can see here is alpha 11 p1 plus alpha 12 p2. That's basically same as alpha 11 p1 plus alpha 12 p2. It's the same as y1. Okay, so you can see that if you write down u as a function of p1 and p2, and obtaining the partial differentiation, you can obtain value for y1. Okay, so you can do same thing for this guy, partial u and partial p2. If you perform this guy, then what you're gonna get is alpha 21 p1 plus alpha 22 p2. And if you compare this expression with alpha 21 p1 plus alpha 22 p2, you can identify that it's same as y2. However, what about if you do like a partial u2 for ua? If you do partial p2 for the expression of ua, what you're gonna get is alpha 1 2 p1 plus alpha 2 2 p2, which could be confusing. However, we already identified that alpha 1 2 is equal to alpha 2 1, and after replacing alpha 1 2 with alpha 2 1, we can identify that it's same as y21 plus y22. Okay, if you get a little bit confused, you can do this practice by yourself, and you're going to realize that by establishing the Maxwell's reciprocal relationship, we can very without any worry, we can do this operation alpha u partial p1 or partial u partial p2 to obtain y2 and y1, because we are guaranteed to have alpha 1 2 equals to be alpha 2 1. Okay, so this is the case for the for the structure with 2-point loading. However, one may ask the question like instead of 2, like what about there is like n nodes on the field. Like for example, we can have like a 10 different point under 10 different load, and what will be the deflection at each point? Okay, so regarding that, like a more really general case, we'll discuss about this problem in the next lecture. But today, let's satisfied with the problem with having two load, because it's still more difficult than single load problem. And to solve two load problem, we have to derive a special relationship called Maxwell's reciprocal relationship, or Maxwell's reciprocal theorem. Okay, so with that, let me wrap up today's lecture, and we're gonna continue our discussion on general n point loading in the next lecture.